No problem. So I think everything's fine. So let's welcome Hendrik Molter, and he will tell us about temporal reachability minimization, delaying versus deleting. So we're looking forward to your talk.
Yeah, thank you for the introduction. Thank you for having me at this workshop. So I'm presenting joint work with Malte and Philip, who are, I think, both also here. And this was just recently accepted to appear at MFCS this year. So what I want to talk about is, as the title already suggests, minimizing reachability in temporal graphs. And I mean, I guess I don't have to motivate this a lot. One motivation is pretty obvious these days. So, for example, you want to contain the spread of some disease. And let's assume this disease is spread through physical contact and that the edges in our temporal network represent physical contact. And then, we want to minimize the number of potentially infected individuals. And we can do this, or let's assume we can do this with the following temporal graph modification operations. So we can try to remove interactions, or we can try to delay interactions, or maybe we can try to reorder some interaction patterns. In particular, for this talk, I will not be interested in removing individuals, or in terms of graphs, removing vertices from the graph. And then there are essentially two assumptions that we can take. Either we know where the outbreak is going to be, or we don't know where the outbreak is going to be, and kind of make a worst case analysis over all possible outbreak locations. And so there has been a lot of work on that already. And in particular, if I miss something here, please let me know. I hope that I didn't miss too much. So the deleting operation has been analyzed quite a lot in the unknown outbreak scenario by Jessica and Kitty and George and Victor. And here, you want to delete vertices, edges from the temporal graph such that for every possible outbreak location, the reachable set is minimized. And we are going to look at this scenario for the known outbreak situation. And the delaying operation was recently analyzed by Diliktas, who I think is also in the audience, and Potapov at AAAI last year. And they look at the known outbreak scenario, but also in various different specific ways. If you have multiple outbreaks, what does it mean? Do you want to minimize the maximum reachability? But I don't want to go into much detail there. And as far as I know, for the unknown outbreak, the delaying operation has not been considered yet. And then I just want to briefly mention two other operations. One is reordering the edge sets, which has been considered by Jessica, Kitty, and Fiona. And also Diliktas and Popatov considered an operation which they called merging. But I also don't want to go into much detail here. And as you can see here, where I put our work, we looked at deleting and delaying. And in this talk, I want to point out a couple of, to us, kind of surprising differences between those two modification operations. And I also have this slide, which I guess here is not super important. So for me, a temporal graph is going to be a fixed vertex set with a set of edges. I have a little example here. And reachability we define via temporal path. So one vertex reaches another one if there's a temporal path from that vertex to the other one. And so this temporal path, they have to respect time. There are a couple of different notions, and I'm actually going to focus on the strict temporal path for this talk. So we consider a vertex to reach another vertex if there's a strict temporal path from the first to the second one. Okay, so what do we know about minimizing reachability by deleting? So the problem, a little bit more formally, is we we know some initial outbreak S, which can be a set of vertices, and we want to delete up to k time edges such as at most R other vertices eventually contract the disease. So in terms of reachability, the reachable sets of the vertices in S, we are interested in minimizing the union of the reachable sets. And here I have a little example. So let's assume the outbreak is at this vertex A here, and I'm allowed to delete 2 edges, and I want to have a reachable set of size at most 2. So what I can do here is delete this time edge between A and B at time 1, and this one between A and E at time 4. And what we can see is that A, well, we can't save A. It was initially infected, and the only other vertex is going to be B, because we are considering strict path. The outbreak reaches B at time 2, and then it cannot continue in a strict fashion anymore. So there are in total 2 vertices A and B which are infected. And what is known about this, that is polynomial time solvable on trees. So that's one of our results for this problem. What was already known by Diliktas and Popatov, even they didn't explicitly consider this version of the problem. If you look at their reduction, it's relatively easy to figure out that it also holds for the deletion variant, even though they look at the delaying variant. So it's known to be W1 hard for the solution size parameter K, and even if the temporal graph has only 2 time labels. And what we also looked at is the second natural problem parameter, which is this R, the size of the reachable set. And we could show that also for this parameter, this problem is W1 hard. And just as a brief reminder, so W1, for those who might not know, for us, it just tells us that we cannot expect, or we do not expect to find fixed parameter tractable algorithms for those parameters. Okay, now let's look at the delaying variant. So let's have this little example again, where we have an outbreak at A, and we are now allowed to delay 2 edges. And more specifically, by delaying for this talk, I'm going to assume that it means I delay by 1 time unit, more generally by a constant. And what we can do here is, for example, we can delay this time edge, so make this label also 2, and we can delay this one to make this label 5. And what we can see now is that A can reach B and E, but none of the other vertices from there, because we arrive at the respective vertices so late that we cannot continue in a strict fashion anymore. So the number of infected vertices is 3, as we wanted in this case, these 3. And what is known, again, this is also polynomial time solvable on trees. That's also one of our results, actually the same algorithm that can handle both of these cases. Again, by Diliktas and Popatov, we know that it's NP hard and W1 hard with respect to the solution size, or the number of edges we want to delay. And to us, a little bit surprisingly, for the reachability parameter, we have fixed parameter tractability for the delaying, while we had W1 hardness for the deleting case. So there's kind of an interesting difference in those 2 problems. And what I essentially want to do in the remainder of this talk is give you an idea how this algorithm here works. Okay. And the first step is that we actually change the modification that we want to do, and show that for our problem it's equivalent. So we essentially, instead of delaying, which to us means we increase the label of the edge, we slow them. And intuitively that means that if you think about transmission times, it takes now 2 time steps instead of 1 to cross an edge. And we can show that for our problem, that's actually equivalent. the delaying by 1 time unit versus the slowing. And what we do is, if we are given now already a set of vertices that are infected, together with the source or the outbreak, of course, we transform this into a flow problem in the following way to check whether we can actually contain the outbreak to those R vertices here by doing at most the K delay or slow operations that we are allowed to do. So let me try to show you how we do that. So let's assume we have this very simple temporal graph here with four vertices, and the underlying graph is a path. And what we do is we transform this into a static graph, which looks a little bit like what is sometimes called a static expansion. So it looks like this. So for every vertex, we create these paths here, which have length, in this case 6, but it kind of depends on the last relevant time step, essentially. And then when there is an edge between, for example, A and B at time 1, we draw this dashed edge here from A1 to B2, where this path would arrive if this edge is not delayed or not slowed. And we draw the solid edge to B3, which corresponds essentially to the vertex, or to the vertex time pair, where a path starting at A would arrive if this edge is delayed. And in the flow problem, these dashed edges are going to have a capacity of 1, and the solid edges are going to have a capacity of infinity. And intuitively, what we do is we add a source for our flow to, so source vertex to the vertices at which the outbreaks occur. So let's assume the outbreak occurs at vertex A. And if now our reachable set, let's say in the beginning it's only A, we want to check whether we can isolate A, then we would go from all these 3 vertices here to a sink, let's call it Z. And then we would try to figure out whether the maximum flow from S to Z is at most K. And if it's at most K, this kind of implies that the flow uses these dashed edges here, and it cannot use the solid edges with infinity capacity. And this kind of implies that if we delay those edges or slow those edges, which is essentially equivalent to removing them from this auxiliary graph in which we compute the flow, then the whole flow uses these edges, which means if we would remove them, then there's no flow anymore from S to Z, which means that we have actually contained the outbreak to the vertices that we wanted to. Now, if we look at this particular example, there's the solid edge here, which means there actually runs an infinite flow from S to Z. So that already tells us we cannot expect that we can, by delaying, restrict the outbreak only to S. But if we now say, let's say our reachable set contains A, B, and C, so we would have flow going from our source to those 3, and only D goes to our Z, so let's ignore this part for now. Then we can actually see that there's a flow of at most 2, right? Because here we can send 1 unit of flow, which can continue essentially like this, and then like this here. And when we can set infinite flow across this edge, but only we can send 1 further unit, which arrives early enough at this vertex C, such that it can continue to the sink. And this tells us that if we delay 2 edges, which in this case would be this one here and this one here, that no flow can arrive at Z anymore. So I hope that kind of makes sense. And now if we found actually that the maximum flow has value at most k, then we are happy. But if it doesn't, then we kind of try to decide what to do next. So how we enlarge our reachable set essentially. So we consider the vertices of our flow networks that leak flow outside of our reachable set. And if we look at this again for a second, so let's say we have again only A as the reachable set, then A1 would be the leaking vertex. If it's A and B, then the leaking vertices of the flow network would be B2 and B3. So these are the vertices that leak flow outside of the reachable set. So in this case, the reachable set contains A and B. Okay. And what we then do is we know that we cannot avoid, so we already know we cannot restrict our flow to the reachable set, or we cannot restrict the output to the reachable set. So one of the leaking vertices has to kind of stay reachable. We kind of have to accept that. And the question is, which is kind of the best one? And there we apply our search tree. And it's a little bit, it's not super obvious to see that this gives us a bounded size search tree. But so what we can do here is whenever I accept that this one is the one I'm going to reach, it's clear I'm also going to reach all the further ones further down. And if this one already reaches too many vertices outside, then I have to discard this, which essentially means that for every vertex in our reachable set, there's only really one of these appearances here which matters, because either I hope this makes sense. If it's confusing, maybe you can ask later. I think I'll just continue for now. So this allows us to do the search tree, and so the overall algorithm kind of works as you probably would expect. So we start with our initial outbreak. We transform it into this flow problem, check whether there's a flow of value larger than k or not. If there's no flow of value larger than k, then we know it's the yes instance, essentially. And otherwise, we compute a small set of neighbors that we have to consider, neighbors of leaking vertices that we have to consider taking into the set of reachable vertices. And as I tried to hint just before, is that this small essentially means that it has size at most r. And then we do a search tree, right? So we try all of them and recurse. And this gives us a running time of r to the r times something polynomial. All right. So to conclude, I guess what I tried to convey is that reachability minimization by time edge modification is a big playing field. You can think of a lot of different modification operations that are well motivated, I guess, and also the way how you exactly measure the reachability is there. You also have some playing ground. What we could show is that if in the setting where we assume that the outbreak is known in advance, there's this surprising difference in the parameterized complexity with respect to the reachable set size that we want to have if I compare the deleting and the delaying modification. And for both versions, we have a polynomial time algorithm if the underlying graph is a tree. And so just one future work that we are currently working at is having an algorithm for trees always raises the kind of obvious question, can you generalize this to bounded tree width or something similar? So this is a question that we are trying to figure out at the moment. Okay, that was everything I want to tell you. Thank you. If you have questions, please.
So